We stopped our last discussion with states of matter, and we talked about how matter is generally classified into two categories: pure substances and mixtures. Mixtures are made up of pure substances that have been mixed together in a non-chemical way. You cannot separate a pure substance by physical change. A mixture can be physically separated in some way. Pure substances have a uniform chemical composition. Mixtures do not. And that really distinguishes these two classifications of matter. When we talk about pure substances, we talk about elements versus compounds. Elements are made up of one type of atom, and compounds are made up of more than one type of atom. So when I look at a particle level representation of different substances, I would say that this is most certainly an element because it's made up of one type of atom, sodium. I would say that this is also an element, even though it has two atoms connected together, that they're the same. So that would be oxygen. Compounds, on the other hand, are made up of combinations of atoms. So you can see this is HCl, right? Hydrogen and chlorine added together. Water, H2O, hydrogen and oxygen chemically connected together with chemical bonds. Furthermore, compounds usually can be broken down into the pieces that make it up. So you can take water and you can break it down into simpler pieces. You can break it down into the hydrogen gas and oxygen gas that makes it up. Elements, you can't really do that because it's already broken down into the type of atom that it is. When we talk about the big distinction between different types of mixtures, we have two different types. Homogeneous mixtures, the prefix homo means same, so it means that it looks the same throughout. There are no distinct layers or boundaries. So for instance, if we look at a particle level representation of what a homogeneous mixture looks like, the particles would be very uniformly distributed and there wouldn't be a layer between them. Hetero means different. Heterogeneous mixtures have a distinct layer. So if I look at a particle level representation, there would be distinct components or layers that we could see. Examples of homogeneous mixtures are things like orange juice with no pulp and salt water. When you mix those things together, it looks consistent throughout. But if you dump sand in water, that actually forms a distinct layer, and those two pure substances are actually separated into different components. Can you come up with at least 3 examples of each type of matter? Pause the video and take a moment to see if you can come up with examples of each type. We said elements are made up of one type of atom. And I'll give you a big hint. When you're coming up with examples of elements, there's 118 that are hanging up on the wall in the classroom. Anything that is on the periodic table as an element is considered an element. Imagine that. Argon, oxygen, iron. Compounds, on the other hand, have distinct chemical formulas, but are still uniform in that chemical formula. So like H2O, water. NaCl, table salt. Glucose, C6H12O6. All of those are compounds. They're pure substances, but they are not mixtures. Homogeneous mixtures have a uniform composition. So we already said salt water. Air is actually a homogeneous mixture because the particles are so uniformly distributed. You have different compounds and elements like argon, you have CO2 and you have O2, but all of them are mixed together without layers. Alloys. Alloys are homogeneous mixtures of 2 or more metals. So if you take silver and you mix it with some nickel, you can make sterling silver. They're actually mixtures of metals that are made at really high temperatures. They're not compounds. Heterogeneous mixtures, mixtures that have layers. Like if you put oil with water. Or if you have a cookie, right, a chocolate chip cookie, those chocolate chips are distinct from the cookie batter. Or a cake, right? A cake has layers. So anything that has layers or has distinct components would be a heterogeneous mixture. This is a little bit more challenging. Can you take these particle level diagrams and determine whether they represent pure substances or mixtures? I'll give you a moment and I want you to try to see if you can identify whether these are pure or whether they're mixtures. This first box is definitely a pure substance because every single one of these components is the same. This is also a pure substance because every single one of these molecules is connected by the same combination of atoms. That's a pure substance. This third picture is also a pure substance because it has all of its particles uniform. However, this would be a mixture because you have different things. This is an element and this is a different compound that are physically mixed together. We could physically separate them, but they're distinctly and chemically different from each other. Let's see if we can look at these particle level diagrams and make a determination as to whether or not these diagrams are representing elements, compounds, or mixtures. This first diagram would be a mixture. How do I know? Compounds, two different atoms connected together, elements, mixed together, non-uniform composition, mixture. All of these atoms are the same. That's an element. I have two different compounds that are mixed together. This would be a mixture. This, however, has a uniform chemical composition. However, the atoms that are connected together are different for the particles that make it up. This would be a compound. In this last picture, I see I have an element made up of one type of atom. I have another element made up of one type of atom, but it is a non-uniform chemical composition. I've got a mixture. How do we separate a pure substance? There's only one way. If you have a compound, the only way that you can separate a compound is to cause a chemical reaction to happen and change it into two distinctly different substances. That is the only way that you can separate a pure substance is through chemical change. Furthermore, I mean, technically you can separate an element like uranium into other elements, but that's not an ordinary chemical change. That's actually a nuclear reaction, which we're going to get to in a later unit. To cause a pure substance to change into a new pure substance, you either have to cause for a compound a chemical reaction, or even for an element, you would have to cause a nuclear reaction to rip that atom into pieces. In our next mini lecture, we're going to go through the different methodologies that we use to separate mixtures.